Incidentally, astronomical occasions on a large scale, billions of miles away from the planet, resonate all through the universe. Presently, a comparable occasion is approaching, causing shock even among researchers. A red giant star at the outer edge of our system's communication spans is sending unpropitious signs across the universe, captured by the James Webb Space Telescope. Cosmologists have discovered a great deal of discouraging information about this epic heavenly body. As renowned astrophysicist Brian Cox gives a grave admonition, a pressing question emerges. Are we wavering on the edge of witnessing a disastrous cosmic explosion that could forever alter the natural night sky? Before delving into any further subtleties, make sure to subscribe to our channel if you haven't already. Now, the lingering question, will this blast occur, influence Earth, and will it be observable from the planet? Keep an eye out as we look into the responses to these enticing questions in this video. In the tremendous span of the universe, where the show of heavenly birth, life, and death plays out with enthralling wonder, one particular star recently directed the interest and concern of both cosmologists and the general public. This star, Betelgeuse, stands out as a red supergiant in the Orion constellation. It flaunts its immense size and age, while its striking ruddy color and varying brilliance have long intrigued onlookers. Recent events have further heightened interest in this heavenly behemoth. As we dig into the essence of Betelgeuse, we find ourselves nearing the very edge of a potentially stupendous event in the star's life cycle. But what do these changes in Betelgeuse's behavior mean? Might we witness the start of a remarkable, grandiose display of impossible extent? Betelgeuse, flaunting a size roughly 1,000 times greater than our Sun, remains a gigantic giant among stars. Due to its size alone, it stretches the limits of human imagination. Imagine a star so massive that, if it were to replace the Sun, its surface would expand beyond the orbit of Mars, wrapping Mercury, Venus, Earth, and Mars inside its heavenly grasp. This tremendous size not only emphasizes Betelgeuse's physical monstrosity, but also indicates its place in the stellar life cycle. As a red supergiant, Betelgeuse is in the sundown period of its existence, marked by expansion and cooling after fusing hydrogen into helium at its core for a lifetime. Questions arise about Betelgeuse's age. Despite the fact that it is still young in human terms, estimated to be between 8.8 and 8.5 million years old, it remains quite old within the framework of stellar existence. Its current color as a red supergiant reflects the culmination of millions of years of stellar evolution, characterized by significant changes from a hot blue star to the great red giant we observe today. The journey of stars like Betelgeuse plays out like a story about entities constantly changing under the relentless forces of gravity and nuclear fusion. One prominent feature of Betelgeuse's current phase is its striking red hue. This dark red shade results from its comparatively cooler surface temperature. In contrast to stars like our Sun, which shines at around 5,500 Kelvin, Betelgeuse's surface temperature is approximately 3,500 Kelvin. This lower temperature enables Betelgeuse to produce red-colored light. However, this color is more than just a visual characteristic. It sheds light on the star's physical condition and the ongoing processes within its vast gaseous domain. Boosting interest surrounding Betelgeuse is its unusual color history. Ancient works from Roman and Chinese sources suggest that nearly 1,000 years ago, Betelgeuse appeared yellow. Only after the 9th century did Arabic researchers describe it as red. This historical shift in color is not merely a footnote in astronomical records. It serves as a signpost in the star's transformative journey. The changing brightness of Betelgeuse adds an additional layer of suspense. As a semi-regular variable star, its luminosity undergoes periodic variations. This dance of brightness has captivated astronomers and stargazers for centuries. Typically, Betelgeuse follows a 420-day cycle and a longer 5-year cycle, noted as far back as 1836 by Sir John Herschel, and possibly even earlier in native oral traditions. However, What truly sets Betelgeuse apart isn't just its shifting brightness, but its irregularity. Unlike many stars that follow predictable patterns, Betelgeuse sometimes deviates from its usual rhythm of changing from dim to bright. This irregularity results from complex and poorly understood processes unfolding within its massive structure. Recently, discoveries related to Betelgeuse have captivated astronomers and global stargazers, particularly when the star experienced a surprising and dramatic change now known as the Great Dimming. It all started in late 2019 when Betelgeuse, a red supergiant shining brightly in the night sky and a significant component of the Orion constellation, began to undergo a mysterious dimming. The dimming was so pronounced that it lost brightness at an average rate of 0.01 magnitudes per day, reaching its lowest brightness by February 2020. Typically visible to the naked eye even amidst light pollution, Betelgeuse essentially faded, so much so that even amateur observers couldn't miss it. However, tracking the activities of Betelgeuse presents a major obstacle: the time conundrum. When we observe a star like Betelgeuse, we're not seeing its current state, but rather its past, due to the time it takes for light to reach us. Betelgeuse is located approximately 725 light-years away, meaning that the light we see today left the star nearly 7 centuries ago. This delay in time complicates efforts to predict and track sudden changes in a star's behavior, as we are essentially witnessing events that happened in the distant past. The dimming of Betelgeuse serves as a stark reminder of the inherent complexities and limitations in cosmic observations and our understanding of the immense scales of the universe. This phenomenon involves the mystery of time itself. The captivating journey of Betelgeuse's astronomical performance was meticulously tracked by Andrea Dupree, the assistant director of the Center for Astrophysics at the Smithsonian and Harvard, along with her team. Using the Hubble Space Telescope, they embarked on a 3-year study to monitor changes in Betelgeuse's outer environment. These observations provided an unprecedented understanding of how a variable star like Betelgeuse behaves, with its regular expansions and contractions resulting in changes in brightness. The striking sensitivity of Hubble to ultraviolet light enabled researchers to investigate the underlying layers of Betelgeuse's surface, which were partially heated by the star's turbulent convection cells. Furthermore, a detailed analysis of the Hubble spectra collected at various intervals throughout 2019 and 2020 made it easier to measure material movement within Betelgeuse's outer environment. Specifically, the study concentrated on the magnesium-2 lines in the spectra, which offer insights into the star's atmospheric conditions. These observations revealed material traveling at approximately 200,000 miles per hour from Betelgeuse's surface into its outer environment. This hot and packed material eventually multiplied by millions of miles from Betelgeuse, forming the precursor to the dust that partially obscured the star's light from Earth's perspective. This ejected material, once propelled into space, began to cool and condense, forming clouds of dust that partially obscured Betelgeuse's light. This phenomenon explained the star's sudden dimming, but it also raised questions about the processes occurring within its core. Could this event be a precursor to Betelgeuse's imminent supernova? As a red supergiant, Betelgeuse is nearing the final stages of its life cycle. Having exhausted its supply of hydrogen, the star now fuses helium into heavier elements such as carbon, oxygen, and eventually iron. This process is crucial because iron fusion consumes energy rather than producing it, leading to a catastrophic collapse of the star's core once it accumulates enough iron. This collapse triggers a supernova, releasing an enormous amount of energy and light that can outshine entire galaxies for a brief period. However, predicting the exact timing of Betelgeuse's supernova is challenging. While the star could explode within the next few thousand years, a blink of an eye on cosmic timescales, it might also happen within our lifetime. The Great Dimming, combined with Betelgeuse's irregular brightness variations, has led astronomers to closely monitor the star for further signs of instability. If Betelgeuse were to explode, the event would be visible from Earth even during the day, appearing as a bright object rivaling the moon's luminosity. This celestial spectacle would last for weeks or even months before gradually fading as the star's remnants disperse into space. Despite its proximity, the supernova would pose no direct threat to Earth, as Betelgeuse is too far away for its radiation or shock waves to cause harm. Yet, the explosion would have profound scientific implications. The blast would enrich the surrounding interstellar medium with heavy elements essential for the formation of new stars and planets. Furthermore, observing a supernova in real time would provide astronomers with invaluable data, enhancing our understanding of stellar evolution and the life cycles of massive stars. In the meantime, researchers continue to study Betelgeuse using advanced telescopes like the James Webb Space Telescope and other ground-based observatories. By analyzing changes in the star's brightness, temperature, and spectral composition, scientists hope to uncover additional clues about its internal processes and the timing of its eventual demise. Ultimately, Betelgeuse's fate serves as a reminder of the dynamic and ever-changing nature of the universe. Whether its final explosion occurs tomorrow or millennia from now, the star's life story offers a glimpse into the cosmic forces that shape the universe and our place within it. As we await this grand celestial event, astronomers and stargazers alike remain captivated by the mysteries of the night sky, eager to witness the moment when Betelgeuse's light will shine brighter than ever before, marking the end of an era and the birth of new cosmic possibilities. Clouds are responsible for the star's dimming. Dupree and her team estimated that during the 3-month event, approximately twice the usual quantity of material from the southern region of the JW hemisphere was shed. This significant mass loss is particularly notable because, like all stars, Betelgeuse continuously sheds mass, but at a much higher rate than our Sun. The magnitude of this mass ejection and the resulting dimming sparked discussions among astronomy experts about whether this event could signal an impending supernova. Betelgeuse's close proximity to Earth, located approximately 725 light-years away, adds to the interest. If such an explosion were to occur, it would be visible from Earth, presenting a fascinating opportunity to closely observe a supernova. But the question persists. What does this dimming event mean for Betelgeuse's future? Does it indicate a forthcoming supernova, or is it merely a transient phase in the star's vast and complicated journey? To shed light on this phenomenon, several hypotheses have been proposed. One theory suggests that the event marks a stage in the supernova process, aligning with the prevailing belief that Betelgeuse is nearing the end of its life cycle. Another widely accepted hypothesis implicates dust, possibly originating from the star itself, which blocked part of Betelgeuse's light. A third explanation examined changes in the star's photosphere, its apparent surface layer, which could affect its brightness. Comprehensive analysis using diverse observational techniques contributed to unraveling this mystery. Spectroscopic examinations revealed a decrease in Betelgeuse's effective temperature, indicating the likelihood of a large dark spot on the star's surface. This theory was validated by observations revealing a temperature minimum of 170 Kelvin during the dimming period, highlighting significant surface changes. Ultimately, the key to understanding this extraordinary phenomenon came from careful observations made by the Hubble Space Telescope. Hubble's precise measurements revealed that Betelgeuse's dimming was likely caused by a significant ejection of heated material into space. This material collided and formed a cloud of dust that blocked part of the star's surface, reducing the amount of light reaching Earth. The formation of this dust cloud was attributed to superheated plasma, which erupted from a large convection cell on the star's surface and traveled through its scorching atmosphere to cooler outer layers. After cooling, this plasma formed dust particles, resulting in a cloud that blocked light from roughly a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, played a crucial role in reconstructing the timeline leading up to Betelgeuse's dimming. These observations detected signs of thick, heated material passing through the star's atmosphere in the months preceding the dimming event. By December 2019, other ground-based telescopes also noticed the star's diminishing brightness, particularly in its southern hemisphere. Initially, this material appeared brighter than usual due to the star's increased luminosity, eventually culminating in the formation of a shadow as the material scattered outward and cooled. The suggestion was that this outward flow and the resultant shadow were responsible for the star's sudden dimming. The actual size of this ejection was remarkable, thrusting Betelgeuse into the cosmic spotlight. The star expelled an estimated 400 billion times the mass usually released in a typical coronal mass ejection. This expelled material was thought to be enough to offset our moon several times over, marking a major event not only for Betelgeuse, but also for our broader understanding of stellar mechanics. But what are the consequences of such a large release? The conventional wisdom holds that red supergiants like Betelgeuse routinely shed mass before reaching the cataclysmic peak of their existence. However, the scale of this release challenges that notion, hinting at a potentially more volatile and unpredictable final stage for these stars. Could Betelgeuse be gearing up for its grand finale, a supernova explosion within the coming centuries? Later research speculated on the timing of such an event, suggesting it may occur sooner than anticipated, possibly within just a few years. Additionally, the concept of the bow shock adds another crucial layer to the Betelgeuse puzzle. As this massive star speeds through space at around 67,000 miles per hour relative to its surrounding interstellar medium, it creates a bow shock similar to the wake that a moving boat's bow leaves behind. This phenomenon arises from the star's interplay between its outer layers and dust and gases from other stars, offering a spectacular display of the star's dynamic behavior and its interaction with the cosmic milieu. But what about Betelgeuse's recent behavior? Its surface cooling and diminished density, observed following the ejection event, have left the star in a disturbed state, even years later. Hydrodynamic simulations point to a connection between the star's convective activities, the mass ejection, and subsequent changes in its oscillation modes. This persistent instability raises questions about the internal processes driving these changes and their potential consequences for the star's future. Additionally, Betelgeuse's measured rate of mass loss surpasses that of many other stars, reflecting the complex interaction of internal forces. Nevertheless, as energy continues to dissipate through shock heating and mass ejection, Betelgeuse's rhythm is changing. The nature of these mass losses points to the star's dynamic and somewhat erratic life cycle, prompting astronomers to reconsider their models of star formation and evolution.